Mr. Hyzer is a fellow of both the Society of Photo-Optical Instrumentation Engineers and the Society of Motion Picture and Television Engineers, and was National Vice President of SMPTE. He is the 1969 recipient of the International E.I. DuPont Gold Medal Award. In 1980, he received the Coleman Memorial Award of Great Britain for the British Institute of Physics. Mr. Hyzer was named Engineer of the Year by the Wisconsin Society of Professional Engineers in 1981. Without any further ado, I would like to welcome William G. Hyzer. Thank you for coming tonight.
Thank you, Jim. Well, it's a real pleasure for me to be here. Can you hear me in the back row? Okay, fine. If you don't, just raise your hand. I prefer not to work with a mic if I can avoid it. I'm going to be directing most of my remarks tonight, I think, to the students in the audience, who I expect it to be quite a large contingency of students. But hopefully that some of the things I say will be of interest to the rest of you as well. But I'm going to primarily concentrate on things that I feel might be of interest to students who would be entering into the field of photo instrumentation. I'm going to be talking a little bit about history, a little bit perhaps about philosophy, and then some of my general experiences in this general field of endeavor. I want everybody here tonight to get something out of this talk. I don't want you to leave saying that you didn't get anything out of it. So I have some postcards up here that I'll pass out after the talk is over, so that no one can leave the room here without saying that they didn't get something from Mr. Hyzer's talk. What I would like to do is discuss a variety of topics within the photo instrumentation field. It's going to be rather non-technical. I would hope that if any technical questions come up that you don't hesitate to ask them, and I will attempt to answer them as best I can when we at the end of my presentation. So I hope that I can generate some questions and that we can get an interchange of ideas between us after I get through talking formally here. Now, I entered this field of photo instrumentation in many respects like some of the students that I had lunch with this noon. I'm talking specifically of Loretta and Sherry and also Jim Taylor. At the time that I entered this field in the late 1940s, there was not a field called photo instrumentation, or it was just called functional photography. I was a graduate engineer, an electrical engineer, but I had an inherent interest in photography. And like many of the students that talked to here at RIT, when I was in high school, I was a yearbook photographer and hadn't dreamed of combining photography with some other field of endeavor. At that time, as I say, this field of photo instrumentation really didn't exist. In the 1940s, it was called essentially functional photography. But then in the 50s, the term came along called photo instrumentation. Let's see if we can have the first slide. Photo instrumentation. Well, actually, it wasn't photo instrumentation in the 40s. Actually, in the 1940s, in the 1950s, it was called photographic instrumentation. It was in the 50s that the terminology changed to photo instrumentation. The graphic was dropped in terms of describing techniques that would relate to video and electronic imaging. Then in the 1960s, the term changed in the late 1960s and early 70s to photonics. Now, photonics is a term that you might not be familiar with. It's similar in many respects to electronics, in that photonics deals with photons, where electronics deals with electrons. The analogy being that in the early days of radio engineering, the applications of radio engineering expanded into other areas involving electrons, and so radio engineering became known as electronics. The same thing happened with photo instrumentation, is that photonics is the field where photons are used as information carriers, just as electrons are used as information carriers in electronics. So photonics is a rather broad field, but generally it relates to imaging systems, that is, utilizing photons for imaging. So this is some of the semantics that have changed over the years, from photographic instrumentation to photoinstrumentation to photonics. Now, semantics can be very important. I recall one time when I was visiting a government installation, and I had a high-speed camera with me. And when I approached the guard, he asked me what I was carrying in the case, and I said, it's a high-speed camera. And he said, well, we can't allow high-speed cameras through the gate. He wouldn't let me come into the facility. So I went around to another gate, where there was another guard, and he asked me the same question, what are you carrying in the box? And I said, that's a high-speed sequential multiple framing device. And he let me through the gate without any trouble at all. So sometimes cameras, the name camera can get you into trouble. And essentially, that's what's changed over the years in describing the field. It has gone from photography into broader terminology that cover the use of photons. So what is photoinstrumentation? Essentially, photoinstrumentation is the utilization of photography or videography or photonic imaging devices as scientific instruments, utilizing the camera essentially as a scientific instrument for recording data and recording information. Now, those of you who are involved in photography, we might think of photography as an art, and we also might think of photography as a science. And supposing we were to plot this so that we had photography at one end, or art at one end of the scale, and science at the other end of the scale, rating from 0 to 100, where would we rate photoinstrumentation in that scheme? Actually, photoinstrumentation would be more of a science than an art, probably up somewhere in the neighborhood of 80 to 85%. Photogrammetry, which is a very technical field within photography, would be in that same general area, somewhere up around 95 on the scale. Portrait photography probably would be down at the art end, maybe down around 10, 15. Commercial photography might be somewhere in the middle. Something of an art, something of a science. So that we have photography covering a very broad spectrum, ranging from art on one end to very profound science at the other end. Now, let me give you a little bit of philosophy at this point. As an engineer, let me define for you my interpretation of what art is, and then let me give you my definition of science. I like to think of art, good art, comprising 3 different ingredients, all of which start with the letter C. I can think of it as a triangle involving 3 different ingredients. And those ingredients are, first, the piece of work has to be creative in order to be a piece of art. Creativity has to go into it. There has to be innovation. It has to be unique and new to be a piece of art. Then craftsmanship is involved. There has to be craftsmanship in producing this particular work of art. Whether it's a painting, or whether it's a play, or whether it's a novel, all of these require a learning experience in the application of a certain amount of craftsmanship. Then thirdly, the third ingredient is that that piece of art has to communicate. If it's a painting, it has to communicate to the viewer. If it's a piece of literature, it has to communicate to the reader. So these are the ingredients that, as an engineer looking at art, this is how I would define the ingredients in art. Now, in terms of communicating, art communicates to the emotions of the reader or the viewer or what have you. Let's talk now about science. I think I can define science essentially the same way. We have 3 C's. We have a triangle that involves 3 ingredients. The first ingredient is creative. In other words, in order to produce a work of science, it has to be unique, and it involves creative talent. Secondly, a piece of science involves craftsmanship. The scientist that does the experimental work and produces this work of science has to apply a certain amount of, or has to utilize a certain mastery of his craft, whether it's in physics or whether it's in chemistry or what have you. It involves craftsmanship. The third ingredient, just like art, is communicate. Science, as opposed to art, has to communicate to the intellect, where art communicates to the emotions. So the ingredients in science and art, as I see it, are very, very similar. They involve creative ability, they require craftsmanship, and they have to communicate something. In one case, art, as I say, communicates to the emotions, and science communicates to the intellect. Now, there's probably another C involved in both of these, and that's curiosity. That's extremely important. And I'd like to emphasize that to those of you who are students, that curiosity is so important in science and it also in art, in generating new ideas and making these things happen. Curiosity is really the sense of wonder. It involves the questions why and how. And that's really what science is all about. And neither science nor art are really definitive fields. They are attitudes toward the world and attitudes toward the truth. So that there's a great similarity between art and science, and it's hard for us to divorce them. And those of us that work in photography probably are interested in both of these phases. And those of us I know that work in the photoinstrumentation field that use photography as a scientific instrument generally appreciate and the application of photography as a tool of art as well. Many of you may have seen this Snoopy cartoon and about with Charlie Brown and Lucy talking about the question of how many words a picture is worth. You probably have heard that Confucius, the Chinese philosopher, said one picture is worth 1,000 words. Now, this is probably the understatement of the centuries, although many Chinese drawings are very simplistic and perhaps they could be described in 1,000 words. But I think that we can say that this is a definite understatement, that a picture is worth many, many, many thousands of words. Just to give you an example, I think that we can assume that we can record about 1 million spatial bits of information per square inch on a photographic film without too much trouble. And since there are about 64 shades of gray that can be recorded, that amounts to about 64 million bits of information per square inch. Now, if we put that in terms of a 35 millimeter frame, it's about 1 1/3 square inches in size, we're talking about 75 million bits of information on a 35 millimeter slide. Now, if we say there are about 30 bits per word, typically, and if we divide 75 million by 30, we get about 2.5 million words per 35 millimeter frame. So you can see that this is quite an understatement. Now, I'm going to be talking about the field of high-speed photography, which is one small area of this whole general field of photoinstrumentation. And with high-speed photography, we can quite easily record 3 million frames per second. That'd be 3 million 35 millimeter frames per second. Now, to put that into perspective, all of the recorded information from the beginning of time, the total accumulation of all recorded information is about 10 to the 16th bits of information. Now, I'm talking here scientific notation for the benefit of those that are not familiar with it. That's a 1 with 16 zeros after it. This would be the number of bits of information recorded throughout all of history. This would be 10,000 treated bits of information. Now then, if it would be possible for us to record this using an ultra-high-speed camera at 3 million pictures per second, we could record about 2¼ times 10 to the 12 bits of information per second. And if we divide that into the total information recorded since the beginning of time, we calculate that it would take about 74 minutes running an ultra-high-speed camera to record all the information ever recorded throughout history, if we did it with that kind of efficiency. So it's a meaningless series of calculations, but it's kind of interesting that photography does have that tremendous information storage capacity, which is one of the main reasons that it's used as a tool of science, because of this tremendous information storage capacity. And then, since we're able to record information very rapidly by the photographic process, because of its sensitivity to light, we can record tremendous quantities of information in very short periods of time. And this is the basis for ultra-high-speed photography and the study of events that move way too fast for the eye to see. Now, I think it might be interesting for those of you who have not gotten out into the real world to understand that engineers and scientists are not the best communicators. If you go to any technical meetings, you'll see this very quickly, that in the slides that they use in their presentations and so forth. And those of you who are working in the photographic sciences should be aware of this and try to help your counterparts in industry or in your work that are going out into the field and making scientific or technical presentations. I quite often give a short seminar to engineers. I don't pretend to be an expert on the presentation or communication of information, but I do put on seminars for engineers to help them in putting on better presentations. Let me give you an example here of kind of a real-world scientific presentation. And we'll start here. If I could have the first slide, please. Let's see. Now, okay. Oh, there's something wrong. I wonder if you'd correct that slide back there for me. Just a minute. Okay, there. That's better. Okay, my talk is on effective lecture slides. Now, I'm going to show you a slide here of a curve that this is an example of a curve showing power versus fuel requirements at various manifold pressures. It's quite obvious if you see these curves what that relationship is. Now we're going to a table which again will illustrate what the population trends are in 5 cities within the United States. And then my next slide here is a blueprint that if you look down in the lower right-hand corner, I'm sure that you can see the area that I'm going to be talking about here very shortly. Okay, now, this is typical of an engineering presentation. You're going to find this in the real world. Now, what did I do wrong? I'm sure that you can pick out many things. I know that I made at least 6 errors in 4 slides here, which is a pretty bad percentage. That's about 150% error. So let's just start over this and go through it again and point out some of these mistakes. First of all, you never start a slide program without a slide and a projector. You don't project light out on the screen if you can avoid it. Instead, you use an opaque slide, so the screen is dark when the projector lamp is warming up. And really, that's so simple. All you have to do is just put a piece of black paper in a slide mask and have that as the first slide in your presentation. So it's a very simple way to solve that problem. So now let's start over again. Here's our upside down slide again, and this is our title slide. There's really no need to turn this slide over because you can't read it anyway. Then with vertical slides, half the slide is on the ceiling and the other half on the floor. So it's a good idea to use horizontal slides whenever possible. Now, to avoid that, every slide should be thumb marked so that they're put in the projector in the proper way. And if they are in some way jarred loose from the carousel, they should be numbered so that they can be put back in the right order. Now, instead of using a title like that, you should use a title that fills the screen, and you could add color for dramatic effects if you wish. Personally, I think in engineering type slides that too much drama is too much. I think that it's nice to have color, but it shouldn't be too flashy for a professional scientific presentation. Now, here's our illegible curve again, which is copied from a textbook. This is a bad place to start. It's better to consider what the audience is going to see, and then redraw that slide in this form here, label it well so that the slide can be seen by the audience. And there's a simple rule for determining whether the print in a slide is of adequate size. If you can take a 2x2 slide and read it without magnification, then chances are people in the back row of the audience will be able to see it. If you can't read the slide with the naked eye, then probably the print is too small, and you better have something that's larger. Now here's our table again. Really has too much data in here for people to comprehend. A better way to accomplish this is simply with a graph. Do it graphically and make this thing in a form that your audience can understand. And then, of course, we talked about the blueprint, which is very commonly, which you'll very commonly see in technical publications. Drawings that you just can't possibly read, even from the first row, and the speaker will apologize to the audience for the fact that probably they can't read it, and then attempt to read it for them. But there are times when neither slides nor words are really adequate to the task of communicating information. And this is an example. Now I see some of you in the audience who are snickering. I use this slide for several ways. I usually use it as one of my first slides in my presentation. First of all, it tells me whether the audience is awake. And it also tests the sobriety of the audience, because if you see people out there that look at this thing like it really exists, then you know that there's something wrong. I did show this slide one time to an audience of lawyers, and they couldn't see that there was anything wrong with that. Now, actually, this picture you may think is fake. It isn't. It's contrived, perhaps, but not fake. I'll show you how this box is constructed. Actually, it's a real picture of a box out in my backyard in Wisconsin a couple of years ago. And the box was constructed like this. If you'll notice that the strut in the foreground here has a slot in it, horizontal slot, and the horizontal top strut has a vertical slot in it, so that from one unique position in space, either a one-eyed viewer or a one-eyed camera, viewing that box from a unique position will see it geometrically as an impossible configuration. Now you know how it's constructed. So I'm going to reverse the projector. We'll take a look at that slide again, and you should see that box as it actually is. But you can't. The image formed on your retina is real, but it's the interpretation of that image that throws you off. So it's a situation where the eye and the brain together interpret this thing as a configuration that really is an impossible geometric configuration. But there are many scientific photographs that are interpreted wrongly as well. And they're interpreted wrongly because those who interpret them did not understand the physics and the science that went into producing those photographs. So it's very important, if you're going to work in the field of photoinstrumentation, where you're using imaging as a scientific instrument, to really understand your craft, really understand the instrumentation, so that you can interpret the results accurately. Now we'll go back to, well, actually this thing is so simple that anybody could build it. Here's a triangle that's an impossible situation. Really what it looks like is this, again viewed from a unique position in space. And this whole thing is so simple that even a child can do it, produce these illusions. So it's a very simple thing to do, but very difficult to interpret unless you understand the optics and the physics and the science of how this was done. So it's very important that in getting into this field of photoinstrumentation that you have a good grounding in the craftsmanship involved with the utilization of these techniques. Okay, now we've seen some of these impossible structures. There's a painting in the Royal Gallery in England. It's a Hans Holbein the younger painting called The Ambassadors, which is painted in such a way that in the foreground there's a skull right here, a very distorted figure. But if you view that photograph from a position in the corner of the photograph looking up, the perspective is such that you will see that skull in true perspective. So actually the artist here used two perspectives. One perspective for the ambassadors, and another perspective, another viewing point for the skull in the foreground. Even artists have used this technique of perspective in very odd and peculiar ways. Now let's talk about some examples where scientific photographs are really, in a sense, fine art. I'm sure you're all familiar with the milk drop photograph of Harold Edgerton's. This symbol has become the symbol for the international congresses on high-speed photography and photonics that is held. These congresses are held every year throughout the world. And this milk drop symbol has been this milk drop is the symbol of these congresses, the symbol of high-speed photography. Now, obviously, when he took that photograph, it was not specifically for a scientific purpose, but in some work that I did with dropping oil on a very hot plate to study the effects of oil droplets when they strike a manifold, a hot manifold, we get the same sort of pattern, and the same sort of milk drop coronet pattern. So even scientific photographs that were intended for an entirely different purpose can approach this beauty of symmetry. Now here's a picture of Tutankhamun's mask, an X-ray photograph, which is really a work of art. It's a beautiful thing. This is a study involving the flow of liquid with dye tracers. And although intended for scientific purposes, it created a beautiful pattern, which comes close to being a piece of art, although the original intent was scientific. So you can see that photography, even when used as a scientific tool, can produce images that are beautiful to observe. This is a thermograph of a blast furnace. You can see the red area is the blast furnace, the hot part of the blast furnace. The blue area is the scaffolding around it. And again, a scientific image that could pass as a work of art. This is an explosive phenomenon. It's a series of pictures starting up in the upper left-hand corner and moving downward vertically along the left side here, and then starting at the center at the top again. That is the order of the sequence. What this is a disk of high explosive. It's a circular disk of high explosive that has been simultaneously detonated at, let's see, 1, 2, 3, 4, 5, 6, 7, 8 points around its periphery. And as the shock wave from each of these points of detonation move inwardly and contact each other, they generate very intense light. In other words, as the shock wave progresses out, as the detonation front progresses out from each of these points, and they collide with each other, they form a very intense flash of light, which gives you something of the illusion of a snowflake in this very fast occurring explosive event. This is a hot nickel ball heated to a temperature of about 2,000 degrees Celsius, dropped into a quenching fluid. And this would be the first picture in the sequence. This would be a later picture in that sequence. Again, producing a very unusual photograph that gets the border on being something that you might call a work of art. This is an ordinary air compressor in black and white, but if we photograph that using a thermographic camera and show it in color, we get a very beautiful pattern like this, from just an ordinary air compressor showing the thermal distribution of energy across that surface of that air compressor. This is a sphere moving at about Mach 3.5 as recorded by an interferometer, the Mach-Zehnder interferometer. The shock wave that precedes the sphere is moving in this direction, that something on the order of 3 times the speed of sound. And this is the shock wave that is produced, and the curved lines that result from the distribution of density gradients in the fluid, which in this case was air, accompanying that high velocity projectile. Again, a very, very interesting pattern, a scientific photograph that comes close to being a work of art. This is a shadowgraph, a simple shadowgraph, of a projectile being fired from a gun. This would be the barrel of the gun here. Projectile, you can see it off to the right. Accompanying the projectile are little particles of powder, unburned powder. Each of these little unburned particles has a shock wave accompanying it. The angle of that shock wave indicates the velocity of that particle through the air. This particular photograph was taken by merely using a point source of light of very short duration to form a shadow on 2 sheets of film. You can see the dividing line between this sheet and that sheet of film. The projectile was fired in front of the film, and when the projectile reached that point in space, a point source of light in the form of a spark was triggered, which then formed this shadowgraph. Just a simple shadowgraph using film and a point source of light. But a lot of information in that photograph in terms of density gradients in the air, the shock waves that accompany the projectiles, and the shock wave from the muzzle of the gun. All of these things are recorded and recorded in such a way that it actually comes close to being a work of art, but yet a scientific photograph. So there is a lot of closeness between science and art, particularly when photography is involved as the recorded medium. I was asked at dinner tonight, what was one of the most difficult projects that I ever had, one of the most perplexing projects. And I said I'd be mentioning it tonight. And that project was to determine how a fly lands on the ceiling. Now you wonder, okay, what scientific significance is that? Probably not a great deal, at least I didn't think so at the time, but it was curiosity that tended to drive me in that direction. There was 2 schools of thought as to how a fly lands on the ceiling. And these 2 schools of thought came from aerodynamicists, who are the people that probably are best equipped to answer that question. But the aerodynamicists could not agree on how a fly lands on the ceiling. There was the half-roll theory, and there was the loop theory. Now, the half-roll theory, the theorists said that the fly would fly along normally, and when it was ready to land on the ceiling, it would take a half-roll, and then land on the ceiling as if the ceiling were a runway, and land in that fashion. The proponents of the loop theory said no, the fly would fly in a loop like this, and then land on that runway, upside down. And so this fight went on back and forth for many, many years. And the proponents of the half-roll theory said that the loop theory was wrong because they could show that aerodynamically a fly could not fly upside down. And so obviously the loop theory was wrong. But the proponents of the loop theory said no, it can't be a half-roll theory because they had calculated that in going through this half-roll that the stress at the wingtips of the fly would be sufficient to shear the wings off going through that maneuver. So this argument went on back and forth. Now, I'm not an aerodynamicist, I'm not a biologist, but I became interested in this, and I thought, well, here's something that perhaps photoinstrumentation can solve. All we have to do is to photograph how a fly lands on the ceiling, and we'll settle this whole question. So it seemed like a fairly simple thing at first, except that flies are not cooperating subjects. They don't fly. They don't land at a certain spot on the ceiling when you want them to. And that was my main problem, as to how to get the fly to land on a particular spot on the ceiling on demand. Now I tried to train flies, and I tried to coax them there with all sorts of attractants, everything that I could think of that would attract a fly, from honey to manure, and none of these things worked. And so this became a project that took not only just a matter of weeks, but it began to take years to find a way to record a fly landing on a particular spot on the ceiling. One thing I needed in this study were a lot of flies. Now, the place to go for flies is the city dump. So I would go out to the city dump with my little net, and I would catch flies, until I began to find my neighbors out there, and they began telling stories about me out there with this net chasing flies. And so I had to devise another means to get flies. And so, being somewhat innovative, I would drive out to the city dump and open all the doors, or all the windows in my car. And then when there are a lot of flies inside, I would close the windows and then drive to some secluded place with my little net and catch the flies inside it. Well, that worked for a while, but I still was unsuccessful in getting flies to land at a specific point at a specific time. Until I discovered that flies, if you put them in a dark environment, in a dark room, and they are attracted to any light that's shining on a vertical surface. So essentially what I did was to build a large box that was dark, so the flies could be put into the bottom of this box. And then I had an illuminated ceiling with a hole in it. This being the ceiling here, which was illuminated, a translucent ceiling with a small hole in it. So the fly down the bottom of the box, when the light was turned on, he'd look up and he would see that ceiling lit up, and he'd see a hole in it. But the hole was too small for the fly to fly right through. He had to land and then crawl through the hole. So now I had a means by which I could get the fly to fly to a specific spot at a time when I wanted them to. So then the only problem was to utilize a photoelectric device that would sense the fly when it began to approach this point and set off the continuity that was required to record it. That would be turn on the lights, turn on the camera, and so forth. And so using this technique, I was able to get quite a few pictures of flies landing on the ceiling. And the upshot of this whole thing was that neither of the two theories were correct. As you can see in this series of pictures here, the fly approaches the ceiling with its two front feet extended above its head, like this. It comes in and it impacts the ceiling with the two front feet, and its forward momentum then carries the fly forward so that its other 4 feet can come in contact with the ceiling. So essentially that's what the maneuver is. The fly flies directly into the ceiling, takes up the shock of impact with its two front feet, and then the momentum carries the fly into a position where all 4 feet come in contact with the ceiling. Now, in studying a variety of different flies, I found that there are flies that are quite athletic, just like people, and there are other flies that are real stumble bumps. They have trouble making this, and they come in at different angles. Now here's one that's kind of coming in at an angle, and more or less catapulting into the position. It hits with one leg, but the momentum still carries it forward, so the landing maneuver is somewhat similar. Here's another fly. This time, the sequence goes from the top down. This fly is flying almost horizontal to the ceiling, but at a slight angle, so it approaches the ceiling at a rather acute angle, with its feet up above its head, like this. And when its feet hit the ceiling, its body swings forward, and all 4 feet then come into position. Here's another example of the same thing, going from the top to bottom. See, its feet are extended way up, and they contact the ceiling, and then the fly swings forward. So that although the maneuver is varied, neither of the theories proposed by the scientists that study this problem analytically, neither of these theories are correct. And that's the important thing, I think, that for those of us that work in the photoinstrumentation field, is that it's an empirical field of study, in which we're really studying the real world and we can look at the real world as it really is. And we don't theorize on it, but we study it using instrumentation techniques to reveal how things really happen. So this was one of the most difficult projects that I encountered in terms of time. And the problem was not one of photoinstrumentation. The one was strictly a biological problem of getting the fly to land at a specific point when I wanted the fly to land at that point. I thought I would talk about another project that might be of interest to you. Nothing that I'm going to be showing here tonight is very profound. Just some applications of high-speed photography that are typical of those that you find out in industry in the real world. Here's a study that I performed here a couple years ago to determine the effects of an impacting particle on safety glass lenses. There were three types of safety glass lenses that we studied. Ordinary tempered glass, then the polycarbonate material, which is used as in safety glasses, and then the common plastic material that is used also in safety glass lenses. We were studying three different types of materials. And we wanted to impact the glasses with particles that would simulate a particle that might be thrown off by a grinding wheel, something of that velocity and that size. To do this, we used instrumentation that's shown here. The whole event is studied by a high-speed camera, high-speed motion picture camera, that is focused on the face of this dummy, this mannequin. The particles were fired by an air gun located here, and we were able to determine that we could control the velocity of the particles to within about 5% using an air gun if we could pump it to a prescribed pressure. The velocity was very uniform. The velocity of the pellet was determined by passing it through a device right up here, which consisted of two photocells, a known distance apart. And as the particle moved past each of these photocells, it determined the time interval required to go that measured distance, and then the velocity was displayed digitally here on this device right here. So that every time we fired a particle, we knew, or a projectile, we knew what its velocity was. The oscilloscope here is used for synchronization purposes. In order to illuminate this event and to get the depth of field required to record this thing at about 12,000 pictures per second, which is what these photographs are taken at, we needed a tremendous quantity of light to illuminate that subject. The illumination was provided by chemical-type flash lamps of the type used years ago in focal plane shutter cameras, number 31 flash lamp. So the synchronization requirements were that the flash had to be synchronized with the firing of the gun, and both of these then had to be synchronized with the camera so that the camera would be at its full operating speed when this whole event took place. The gun was fired with a solenoid, just an electrical solenoid that operated the trigger, and the synchronization was achieved in that way. So it was a fairly simple device. It was illuminated, as I say, by flash lamps, chemical-type flash lamps consisting of aluminum foil and an oxygen atmosphere that put out something on the order of about 3 million lumens of light. And this permitted these pictures to be taken at 12,000 frames per second at a relative aperture of around f11 to f16. This would be the setup right here. Showing the arrangement of the lamps. This is the device here that measures the velocity of the projectile. The BB passed through that measured distance, that device. Okay, now let's see the 16 millimeter film. There's going to be some other sequences on this as well. I only brought one film with me. It's one that I used at another talk, and I haven't re-edited. So if you could start the 16 millimeter film, please. And I'll comment on some of these things as we see them. Now, one of the things that the high-speed photographer does is to photograph breaking of a light bulb, and usually the wink of an eye. So I'm going to show you a wink of an eye, which takes about a sixth of a second.
Could you touch your light, please?
Yes. And of course, you're familiar with the pictures of milk dropping into coffee. Everyone who works with high-speed cameras does this at one time or another. Liquids are always interesting to photograph because of the fluid nature of the phenomenon. It's always different and generally interesting. That particular picture there was recorded at about 3,000 pictures per second. This is a photograph of a ballpoint pen, which is interesting because it shows a phenomenon that was known in the pen industry as gooping. You notice that when the ball changes direction, when the ball rolls across the paper, it builds up ink at the equator, at the pole of the ball. And then when it changes direction, it will drop that accumulation of ink onto the paper as a drop. And that gives you irregularity in the line. And so you can see these drops forming when the ball changes direction. In this case, the pen was not moved across the paper was moved beneath the pen was stationary. Again, not a very high speed phenomenon, although this was photographed at about 2,000 pictures per second. Actually, the rotation of that ball is very, very high speed. But, now, if we could refocus that, please. I think it looks a little bit out of focus. Now, this first picture is in real time. It's taken at 24 pictures per second, firing the projectile into the eyeglass. You'll see it occurring very, very rapidly. Much too fast for the eye to see. There, it's all over. Here are the high-speed sequences taken at about 12,000 pictures per second. The first is glass. This is safety glass, tempered safety glass. Next, we'll see CR39 plastic, which is used in safety glass lenses. Notice that it doesn't pulverize like glass does. What it does, it forms pie-shaped segments with the point all going into the eyeball. Now, these are the type of safety glasses that are used in industry. This is polycarbonate. So if you wear safety glasses, I think now you would probably want to wear polycarbonate safety glasses. This is a 38 caliber bullet going through a glass of water. Using conventional optical cameras of the rotating prism type are not really adequate to the task of recording bullets. If we had a stop motion projector here, we could look at this at a frame at a time, and we could see about 4 frames of the bullet. But it's an effect that takes place very, very rapidly. This is pouring wine into a wine glass. the fact, when my wife was asking me to pour water in the water goblets, I was getting water on the tablecloth. Couldn't understand. I didn't pour water on the tablecloth. I really didn't see it. But then I discovered that what was happening is that the water was going down one side of the glass and actually going out the other side and onto the table. So I tried to arrange this with wine glasses. I haven't been able to do it any further than just 2 glasses. Okay, let's see where we are. Let's go to the next slide. Now, this is the picture that I have on a postcard that I'd like all of you to have. It's a picture of a .38 caliber bullet coming directly out of the muzzle of the gun toward the camera. Now, I've had people ask me, you know, what happened to the camera? And they never ask what happened to the photographer. They always ask what happened to the camera. And actually, nothing happened to the camera. This was very carefully staged. I did this picture for a television show, PM Magazine, and was doing a series on some of the work that I was doing, and they wanted a subject that they could show how high-speed photography was used, and it would be something that the general public would appreciate and understand. And I said, well, how about taking a high-speed picture of a bullet coming directly at the camera? And they thought that was great. So I did all this while they were filming this thing for the television show, and that's how that picture evolved. The technique really is to fire the gun into a mirror. There's a sacrificial mirror located here up to the surface. The camera is located at this position, looking into the mirror and aligned with a laser so that the camera, the optic axis of the camera is aligned up right with the right end of the pistol. And then the pistol was fired, and a strobe here, not very short duration. This was something on the order of about 15 microseconds, about 15 millionths of a second. Because we didn't need extremely short exposure times because the bullet was moving directly at the camera. So it was not, there was no transverse motion. It was, all the bullet was doing is increasing in size as it approached the camera. So it really got the field of limitations, really determined what sort of flash duration was required. So 15 microseconds was quite adequate to stop that bullet from flight. Now, one of the problems I had was that some of the first pictures that I took, I couldn't find the bullet. And there wasn't a hole in the mirror, but I couldn't find the bullet. The pistol had obviously fired, but the bullet was invisible. This is a schematic of how this was done. The pistol is located here. There's a mirror. The bullet stop, which is nothing more than just a box filled with gravel. And the camera located in this position so that it is looking right down the muzzle of the gun. The reflector was used to reflect light onto the dark side of the hand and the pistol for just illumination purposes. And what I discovered, the reason I couldn't find the bullet, is that when the bullet moves down the barrel of the gun, it pushes out smoke ahead of it. Now, this was a 4-inch long barrel. So there was a 4-inch column of smoke that preceded the bullet down the barrel. So that you wouldn't see the bullet until it got out at least 4 inches from the end of the gun, because it was buried in smoke. So here's a sequence of pictures. This first one was taken just as the bullet emerged from the barrel of the gun. You can't see the bullet. The next one is at 100 microseconds, 100 millionths of a second later. You still can't see the bullet. Here the bullet is just emerging after about 400 microseconds. It's gone 4 inches approximately. It's just beginning to emerge from this column of smoke of the barrel of the pistol. And then this, of course, is the picture that we saw before. Just a little over 400 microseconds after the bullet emerged from the muzzle. So these are things that you don't understand until you begin to take pictures. And this particular picture has been been of great interest to people that work in the ballistics field because it demonstrates a lot of the things that they knew was happening but never had really observed before. I'm quite often asked what that lace-like pattern is up there, that yellow lace-like pattern. Essentially what that is burning powder. A particle of burning powder that traces out that pattern because the photograph was taken in a darkened room with the camera shutter open. And the photograph was taken by a short duration flash which fired while the camera shutter was open. So that any self-luminous subject, in this case burning powder, would expose the film. And since that burning particle was moving in that circular fashion, it traced out that image of, that you see in the picture there. So every photograph generally had that kind of a pattern, but in a different location that was quite random. Now I'm going to talk very briefly. I'm going to leave some time open for questions here. I'm getting near the end here. One of the applications that seems to be opening up for people in the photoinstrumentation field is in legal photography. You're probably familiar with the problems involved with perspective in photographs. Here's a picture taken with a 28mm lens of an accident scene. If we take that same scene with a 135mm lens, we get an entirely different appearing photograph, which presented to a jury could give an entirely different point of view in terms of the geometry of this particular accident. So people who are experienced in the technique of photography and understand the optics and the chemistry and so forth, there's applications for work in this legal area with attorneys and with insurance companies and so forth in analyzing photographs for legal purposes. Here is a photograph which doesn't look like much, just a couple of black areas with a little spot in between. But it's a very valuable photograph from a legal point of view because this is a set of contacts, electrical contacts, with a particle between the contacts that have prevented those contacts from closing and resulted in an accident. So here's a photograph that is of great value from a legal point of view because this switch was involved in a malfunction. And the photograph provides all of the evidence needed to show why that switch malfunctioned. It's that particle that separated the contacts and prevented electrical continuity. This is a photograph of a fire, one that I was involved in, and it's illustrative of how you might utilize your photographic abilities to analyze a photograph and for legal purposes. This fire was a printing plant, and this is only one of a number of photographs that were taken during that fire by photographers from 3 different newspapers that were randomly taking pictures at various vantage points of this fire as it progressed. After the fire was over, the attempt was made to determine how the fire progressed through the building. This became a very important thing. We wanted to know where the fire started and how it progressed through the building because there was evidence that there were highly volatile and combustible materials stored in there that tended to propagate the fire. And so they wanted to determine just what the chronology was of the fire as it progressed through the building. Well, we had all of these photographs taken by 3 photographers in a random fashion. And I was given the task to try to determine what the chronology of the fire is. Well, this was very difficult to do because these photographers didn't take notes. All they had were their images. But very peculiarly and very luckily, on the night of the fire there was a full moon. You can see the moon up there at the top of the picture. Now, the moon subtends an angle of about 0.53 degrees. It varies depending upon the time of the year and so forth, but it can be calculated as to what angle the moon subtended. So it was possible for me, because I knew that it subtended 0.53 degrees at this particular time, that I could determine the focal length of the lenses used in all of these photographs. Even though the photographers were using zoom lenses, the image of that moon would determine, the image size of that moon on the photographic film would determine the focal length lens that was used. Then, the moon is moving across the sky as this fire progressed. So it was possible then, by using those pictures in which the moon appeared, to determine at what time that picture was taken by the position of the moon in the sky. So now then we could determine the chronology. And now the moon didn't appear in every picture, but these pictures were on a continuous strip of film, and every now and then they would get a picture of the moon in it, and so we could establish a particular time that that picture was taken. So then putting all of these together, we could develop a chronology, just based on the fact that the moon was visible in those pictures, and the moon, of course, follows a mathematical position can be mathematically determined as a function of time. So this is another example of how photographs can be analyzed for legal purposes by someone who is familiar with the photographic process and with optics, and in this case, a little bit of astronomy. Here's another example of a photograph of a scene that was taken by an amateur photographer in Florida. And you see the shadow of a palm tree over here. Well, at some later point in time, there was an accident involving that palm tree, but the palm tree had disappeared. It was gone. Nobody knew exactly where that palm tree was, and they wanted to locate its position. All we had was the shadow of that palm tree on the wall. So there's enough information in this picture. If we would go back to the site and determine the sizes of these things, that, like this plaque on the wall and this bubbler here, this water fountain, we could go back and see and determine their positions. Then we could calculate where that palm tree was located. Let me explain how that was done. I'm going to go 2 slides ahead here because I guess I don't have it there after all. I thought I had another slide in here that would illustrate that, but I don't, so we'll do it in this way. You can determine any position on a plane if you know 4 points on that plane. In other words, if you take a photograph of a plane surface like a wall or a floor or a street, and there are 4 known points in the photograph, and those 4 known points in this case are the 4 corners of that plaque. We know the size of it, and so we know where those 4 points are. So from that information, we can calculate the location of any other point on this wall. So now we have a shadow of the palm tree. We know the direction that the wall is oriented, and so we can determine at where the shadow is relative to the tree. The other thing that we need to know is how far away that tree is from the wall, and we can determine that by determining the density gradient across the shadow. In other words, the shadow across the density gradient across the shadow of the tree here is less sharp than this shadow here. It's very close to this wall here. So that the sun subtends an angle of about ½ degree, and so it does not produce a sharp shadow. And the degree of unsharpness depends upon how far that tree would be located from the wall. So we could estimate that distance, and from that information could determine where the tree was and how far away it was from the wall when that particular picture was taken. Now, in order to do that, we have to know that the position of the sun. That could be determined by this shadow here from this water fountain, which exists there today. So we know that this picture was taken at a particular time of the year, and we knew the time of day that picture was taken, and also the location of the sun. And so from that information, we could calculate the position of the tree. So this is another example of analyzing a photograph to get information that would not be readily apparent to the uninitiated eye. So this is another area of employment for those of you who are working in the field of technical photography that you might want to consider is in this area of analyzing legal photographs, or using your knowledge of photography to analyze photographs. Now, if we could change the slide tray, I'd like to show you a series of ballistic photographs, which will more or less terminate my talk, but I'm certainly available here to answer any questions that you have. And as soon as we get the tray on, we'll start with the first slide. This is a series of pictures of projectiles going through a variety of different subjects, such as apples and oranges and a variety of common objects. Now, I'd like to show you how we set up these photographs, the apparatus that we used for making these series. We built a large light box that's shown here. And if you could sharpen up that projector, I'd appreciate it. I think it's a little bit out of focus. That's good. We built a light box, painted it white inside to get plenty of reflection. The rifle was located outside the box, and we would fire the bullet through the box into a bullet catcher down at this point right here. So the bullet would actually pass through the box and strike the object that we want to photograph. There was a light source at this position here, attached to the outside of the box. This would be a micro flash, having a duration of about 1/3 of a microsecond. That's about 1/3 of a millionth of a second. Located here, there was another light source back here that provided backlighting. And then the camera looked through another window on this side of the box at the subject. The light source and the camera were under large black cloths to exclude light, so that when the cover was put on the box, it was totally dark inside. That permitted us to open the shutter of the camera without exposing any film. The bullet then was fired, and when the bullet reached the object at the proper instant, the flash would be fired and a photograph made. Again, as I say, the duration of the flash was about 1/3 of a microsecond, 1/3 of a millionth of a second. We're looking at these bullets from a side view, so they are moving anywhere from approximately Mach 1 for a 38 caliber pistol bullet to something on the order of 2 to 2.5 times the speed of sound for a rifle bullet. Synchronization was achieved by utilizing a microphone. I think I have a picture here, the next picture that shows the position of the microphone. Here's the microphone here. As the shock wave came out of the muzzle of the gun, it moved at the velocity of sound, and when that shock wave reached the microphone, that triggered the flash to fire. And that was our means of synchronization, simply utilizing the speed of sound as a time delay device. Now, if the bullet was moving at Mach 1, that is at the speed of sound, then it would be moving, the bullet would be moving at the same velocity that the shock wave would be. Therefore, we would place the microphone at the same distance from the muzzle of the gun as the object that we were going to strike with the bullet. But in this case, the bullet was moving at something greater than the speed of sound, and so then consequently the microphone would have to be placed in closer to the rifle than the object that we were going to be photographing. So that's how the synchronization was achieved. To test this for each subject, generally we would take a Polaroid photograph to determine that the position of the bullet after it struck the object was about where we wanted it to be. And then, once that was determined, then the film camera would contain color film was put into the recording position and we would take photographs. You can calculate the position of the bullet relative to the gun and set the synchronization up that way, but generally you want to photograph the bullet after it passes through the object that you're striking. And so objects have different degrees of density and different resistances, And so it does take some experimentation to set up to fine-tune the synchronization. So now let's run through these series of pictures showing bullets going through a variety of different subjects. Here we have a bullet going through a tomato. Most fruit, when you strike it with a bullet, you'll get this jet that comes right up out of the top. It's very common in apples and oranges and tomatoes, juicy things like that. This is a papaya, an egg. Now you can probably realize right now why we did this in a box outside. We didn't do it in a lab. We didn't even consider the possibility of doing this inside the laboratory. So all of this was done outside, in this big box. Everything was confined in the box. And then after each one of these firings, you have to clean up this mess. This is an onion. And a banana. This is a candle. It's interesting that the liquid that comes out of that ketchup is not red, it's white. You think that it would be red. The bullet here has not emerged yet. In some cases, with these types of photographs, you like to show the bullet, the actual bullet, but sometimes by the time the bullet comes out of the object, the drama is gone in terms of the distortion of the object itself. So you have to vary these things. This is a split of champagne. This is this particular laxative works fast as a bullet. This is a pepper. Ice cream cone. Terrible way to waste an ice cream cone. These are three streams of water in which the bullet passed through the three streams of water. These are suckers on a stick. This is interesting because you'll notice this is powdered sugar. And this is almost powdered sugar. And the bullet has just begun to impact this one. And that will soon be powdered sugar. That was one of the messiest things we ever did because it just converted those things into just sugar everywhere. It's a pear. A cucumber. An artichoke. A bar of soap. In fact, I like bars of soap so much I even did it again. It's a lemon. It's a bowl of jelly beans. You'll notice that the bullet is now 90 degrees to its original trajectory direction after going through that beaker full of jelly beans. I come from Wisconsin, and you probably would like to know this is how they put the holes in Swiss cheese. I call this cutting the mustard. Here a bullet has penetrated this first light bulb, and you can see that it's now inside the second tip of it here and the tail end of it there. Everybody has to have their Twinkies. You couldn't exclude Twinkies from this. This is a slosh. And you probably want to know the fate of the bullet after passing through all these subjects. It ended up in this potato. There it goes. Didn't even come out. Okay, what I've tried to give you here tonight is some kind of an insight into my experiences, at least, in the high-speed photoinstrumentation field. And I'd like to give you some, those of you who are students, that like to encourage you to use your ingenuity and curiosity to apply your talents to this field and expand it beyond the limits that any of us imagine that it can be expanded beyond, because you certainly have that capability. It's a fascinating field, one that I have found to be continuing interest in, and I'm sure that you'll find it to be the same for you. So thank you, and I'll be happy to answer any questions that you might have. Whatever. Yes?
Does the fly stick on the ceiling, or does he grab hold of it?
Well, he sticks on the ceiling. The fly has little hairs on its feet called clovilli that are very fine hairs, and you'll notice the flies are always putting their feet in their mouth, and they get this mucusy-like material on their hairs, and so they essentially stick on the ceiling. Now, I learned something about flies tonight that I didn't know before. I'm going to reveal that to you. I had dinner tonight, and Jim here was telling me something. He said, you know how you get flies to fall off the ceiling? And he claims this is true. You take a goblet, a glass, and you put a little bit of liquid soap in it, just a few drops of liquid soap in it. And then you hold that up close to the fly on the ceiling, and the fly will drop into the jar. And he said he's trying this, and it works. We don't know whether the fly just gives up and just falls into the jar, or whether they fly down into the jar and get stuck in the soap. He couldn't answer that question, but if you don't study this thing, I am, because I found this to be fascinating. And he claims that it does. So if you want to get a fly off the ceiling, you put a little soap in a goblet, and just hold it under the fly and it will fall into the jar. Any other questions? Yes?
Your trick with the line coming down into the goblet. I wonder whether if you had a clear hole with a sinusoidal shape, whether it would continue and you could do more than two.
Well, that's a good point. I haven't really explored it that far. I'm sure that the shape has something to do with it, because the wine is falling as laminar flow, and it's when it's drifting hour drives down there and hour drives back. And I will have the power. And I just dictate it. My secretary types it up, and generally we'll go through about a half hour. No, I don't. It's something I don't travel too much.